In Part 6 of the Class A Takeoff lesson, you learnt about how to work through the performance graph to calculate the various performance masses. In Part 7, you will learn how to work out what masses to select for the takeoff, and then using that mass, you will work out how to calculate the takeoff v-speeds. Using our example values from each of the graphs we have just studied, shown here is a list of the masses that we have calculated so far. The question now is, which mass do we use as our takeoff mass? Let's work through each mass again. If our mass is more than the field limit mass, then it is impossible to meet the field length requirements and a safe takeoff cannot be completed. If the takeoff mass was greater than the climb limit mass, then the aeroplane cannot attain the minimum climb gradient requirements. If the takeoff mass of the aeroplane exceeded the tire speed limit mass, then the tires would disintegrate on takeoff. And lastly, if the takeoff mass was greater than the obstacle limit mass, then the vertical obstacle clearance requirements cannot be met. However, it is possible to exceed this last mass provided that the aeroplane clears the obstacle by a set horizontal margin. We'll grey out the obstacle limit mass because it is possible to be heavier than the obstacle limit mass. From the masses left, there is only one mass that can be selected for takeoff, and hopefully now you will understand that this has to be the smallest of the masses shown. In our example, it is the climb limit mass of 56,000 kilograms. This mass is then called the performance limited takeoff mass, and is the lowest of all the masses. In this case, the lowest performance mass was the climb limit, and therefore the performance situation is described as being climb limited. However, our example uses a flap setting of 15 degrees. Shown on screen are the limiting masses using 5 degrees flap setting. From the list of masses for 5 degrees flap, you can see that the lowest mass is the obstacle limit mass. But remember, the aeroplane can be heavier than the obstacle limit mass so long as the aeroplane clears the obstacle by a minimum horizontal margin. So again, this mass can be excluded from the list of limiting masses. Therefore, the most limiting mass is the field limit mass of 57,900 kilograms. This would be called the performance limiting mass. The takeoff performance in this example is described as being field length limited. If a pilot were in a position to choose between setting 5 or 15 degrees flaps, then the higher performance limiting mass of the two would be selected, since it allows for the greatest mass and therefore the greatest potential revenue. Therefore, in our example, a 5 degrees flap setting would be used, and the performance limited takeoff mass would be 57,900 kilograms instead of a mass of 56,000 kilograms. Having calculated the maximum performance limiting takeoff mass of 57,900, it must then be compared to the maximum structural takeoff mass. For the 737 specimen aeroplane we have used, the maximum structural mass is 62,800 kilograms. To use a higher mass than this would seriously endanger the structural integrity of the aeroplane. Therefore, the lower of the performance limiting mass or structural limiting mass is chosen as the takeoff mass. This mass is called the regulated takeoff mass, and this is the mass that is selected for takeoff. In our example, the aeroplane is performance limited, not structural limited in the takeoff. Having chosen the regulated takeoff mass of 57,900 kilograms, we're now able to select the takeoff v-speeds of v1, VR, and v2. Before we calculate these speeds, the speed band needs to be selected. At the bottom of page 17 of section 4 of CAP 698 is a small table which we saw earlier. This table is the density correction table for the takeoff V-speeds. From our earlier examples, we had a temperature of 25 degrees Celsius at an aerodrome pressure altitude of 2,000 feet. Therefore, in our example, the speed band to use is speed band B. Turning over the page to page 18 in CAP 698, you can see the speed tables. There are two sets of speed tables. The one on page 18 is for 5 degrees flap setting, and the one on page 19 is for 15 degree flap setting. Our example is using 5 degrees flaps with a regulated takeoff mass of 57,900 kilograms. On the speed tables, for a 5 degrees flap setting, identify the column for speed band B. The left-hand side scale of the speed table is mass. Notice that our example regulated takeoff mass of 57,900 lies between 55 and 60,000 kilogram marks. Therefore, interpolation must be used when working out our V-speeds. V1 for 55,000 kilograms is 138 knots, and for 60,000 kilograms V1 is 145 knots. Correct interpolation of 57,900 kilograms would make V1 equal to 142.06 knots, which should be rounded, but we will do this shortly. Carrying out the same exercise for VR makes VR for 57,900 kilograms equal to 145 knots and V2 equal to 152 knots. However, V1 must be corrected for slope and wind as shown in the table at the top of the page. For a 2% upslope and a mass of 57,900 kilograms, V1 must be increased by 1.79 knots. For a 20-knot headwind, V1 must be increased by 0.5 of a knot. Therefore, the total correction to V1 is to increase it by 2.29 knots. Adding 2.29 knots to the original V1 of 142.06 knots makes V1 144.35 knots, which is rounded to 144 knots. Having finished with V1, VR, and V2, there are two other speeds to check through. The first of these is VMCG. Looking further down the page, you can see the table for calculating VMCG. Using 25 degrees Celsius and 2,000 feet as our pressure altitude would make VMCG to be 112 knots. Remember from our theory, V1 must not be less than VMCG. Lastly, the speed VMBE also needs calculating. The graph for this is on page 15 of section 4 of CAP 698. We have already described this graph and how to use it. If we use our example airfield conditions of 2,000 feet pressure altitude, 25 degrees Celsius, and a regulated takeoff mass of 57,900 kilograms, then VMBE is 175 knots. However, there are some corrections to make. In our example, we had a 2% upslope. This means we need to increase VMBE by 4 knots. There is also a wind correction to be made. In our example, we had a 20-knot headwind, and this means VMBE must increase by 6 knots. The total correction would increase VMBE to 185 knots. All the relevant takeoff V-speeds have now been calculated based upon our regulated takeoff mass of 57,900 kilograms.